All right, hi y'all. We'll get started. We'll see if anyone else comes today. Not sure. But in any case, if y'all have questions, feel free to ask them. We have a test on Monday. So we can go over anything from that, or you can just ask your specific questions if you have any. And then I will likely do a review session on Sunday as well to do any last minute questions that you may have. So just let me know and I will happy to oblige. Feel free to take yourself off of mute or just ask in the chat. Yeah, great question. So when we're looking at ground state electron configurations and excited state, ground state, you can say that this is directly from the periodic table. Okay, so if we have something like, we'll just use a periodic table here. Right, so if we have something like we'll say calcium, right? Calcium here. If we have calcium, then that means that from the periodic table in its ground state, you're going to do H, right? Start with H, 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? We're just going to build and go across left to right the periodic table, right? So calcium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Or you can write it as the noble gas configuration, where you're going to take the noble gas right before it, which is argon in this case, right? That comes right before calcium. And therefore, you're going to have argon and then 4s2. Okay, that would be the ground state. For an excited state, we just need to take one of those electrons and move them up into a higher energy level. So you could take calcium and we're just going to say argon 4s2, right? We're just going to write it this way. We're going to take argon 4s2, but instead we're going to push one of those s electrons into a higher energy level. So what comes next is, right, 3D. So then we can say it would be argon 4s1 and then 3d1, right? That's a potential excited state. Right, so you can think about, so ground state is directly on the periodic table. Excited is anything higher than the highest energy level that you have, right? You could have put it in a 4p orbital, or you could have put it in a 4d orbital, something like that. It just needs to be in a higher energy level. So another one could have been argon 4s1, 4p1. You could have also done that as well. Right, and you can do that for anything on the periodic table as well, right? If you have lithium, right, you can have 1s2, 2p1. You could bump this up to 1s2, 2p1, right? So now you've gone from the ground state to the excited state. Right, think about the ground state as U as rest, your lowest energy that you have, right? You're sleeping, that takes the least amount of energy. And then your excited state is when you're up, moving around, have a little bit extra energy because you have a higher energy level in that case. Any questions there? All right, any other questions? Yep, absolutely. So when we look at something like diamagnetic and paramagnetic, if we have diamagnetic, does this mean, I guess, which one, how do I want to ask this question? Which one has a magnetic field, a diamagnetic field or a paramagnetic field? Right, which one acts as as a magnet? Dia or para? Good, right? So diamagnetic means not magnetic. Para means magnetic. And what we're looking for is that not magnetic has paired electrons, where magnetic has unpaired electrons. So if we're looking at an element's electron configuration, if we have something in the p orbital, let's say, and we have 3 unpaired electrons, is that going to be dia or paramagnetic? Good. Yep. This one's going to be paramagnetic. Okay. What if we had something in the s orbital that had 2 paired electrons? What is this one going to be? This one would be diamagnetic. Okay. What if we had something in the d orbital that had 1 paired electron and 4 unpaired electrons? This one would be para. Yep, this one is also going to be paramagnetic. Anytime you have unpaired electrons, it will be slightly paramagnetic. It just depends on the extent of paramagneticity, right? If that's a word, if it has 5 unpaired electrons, that's going to be more paramagnetic than if it only has 4, right? And if it only has 3, then it's going to be less paramagnetic, even more. So if you see any sort of unpaired electrons, it will be paramagnetic. It's just to what extent is it paramagnetic? So the more unpaired electrons you have, the more paramagnetic. The more paired electrons, the less paramagnetic, and the more diamagnetic. Does that make sense? Does that help? Great. Any further questions on that one? Alrighty, any other questions? Great. Yeah, anything specific about them? Or just like a general? Yeah, absolutely. So when we talk about intermolecular forces or IMFs, this is like This is the interactions between molecules. Okay, so does anyone know our strongest IMF? Or you can either tell me the strongest or you can tell me what IMF everything has. Yep. So we have hydrogen bonds are going to be our strongest. In terms of the same molecule having intermolecular forces with itself, right? Intra is going to be an ion in the dipole. Inter is between molecules. So H bonds are going to be our strongest. What creates a hydrogen bond? Perfect. Yep. We need to have a H directly bonded to oxygen, nitrogen, or fluorine. So you can have HF, you can have HO, or you can have HN, but COCH does not work. Okay. So some examples of hydrogen bond, right? Water and ammonia. Right? Both of these will hydrogen bond. What's another IMF that we have? Ion dipole is another IMF. When we have an ion dipole, we have something like, we have an ion, which is a full charge. And we have a polar molecule, which has partial charges. So that can be something like sodium coming in close contact with HCN. Right, this would be an ion dipole. We have a full charge on our sodium, and we have slightly negative and slightly positive here, so we have a dipole there. Partial charges only happen with covalent bonds, correct? Right, so whenever you see an ion dipole, you need to have something that is always polar and something that is an ion, right? That creates an ion dipole. What other IMFs do we have? Yeah, and so another example could be chlorine and carbon fluoride. And technically this guy here would look like Na plus and NCH, because you want your ends of the dipoles to match up to your ion. Yep. right? The CF has different electronegativities. So the fluorine will pull its charge or the electrons closer to the fluorine, therefore creating a partial negative charge and a partial positive charge on the carbon. So that chlorine that's negatively charged will be attracted to that partial positive charge a little bit more. Does that help with that question? Great. Okay. Someone said dispersion forces. When do these occur? Yes. Yep. These are always happening. These are in both polar and non-polar compounds. So something like oxygen, or something like nitrogen, or something like CH, right? All of those would be non-polar and they would have dispersion forces. But when we talked about, right, water or ammonia, those would also have dispersion forces, even though they also have hydrogen bonds. Yes, London dispersion forces is just shortened to dispersion forces. Yep, they are the same. Okay, what other IMFs exist? Good. All right, so then we have dipole-dipole. When do these occur? Perfect, right? This happens with polar molecules. So something like carbon oxygen or HS. I'll do. Right, those are going to be polar. This is going to be polar. That was and then something like HCN. Those would all be polar and have dipole forces. Yes, dipole forces can occur at the same time as ion dipole forces, and hydrogen bonds can also occur at the same time as dipole forces. Right, you can have multiple intermolecular forces working at the same time. And a hydrogen bond is actually just a stronger version of a dipole interaction. So, it's not like you can only have one of these, they can both be happening at the same time, yes. Because if you have like an ion dipole, you're not gonna have an ion and a dipole, right? It's not gonna be just those two molecules. You'll have multiple of those in solution. So everything that has all those dipoles can have dipoles with each other, in addition to having interactions with the ions that are also in solution. Perfect. Okay. Any other ion or any other intermolecular forces that we can think of? Yes, the center of the Lewis structure is always the least electronegative. As long as it's not hydrogen, right? Hydrogen can never be the center, even if it is least electronegative, even if it is the least electronegative. Correct. Yep. Just be careful with the compound that's being asked, right? If you see something where it's like something like this, right? That does not mean that carbon has 3 hydrogens, a carbon, an oxygen, an oxygen, an oxygen, and a hydrogen attached to it, right? That's not what's occurring. What this is saying here is that you want carbon and 3 hydrogens, then another carbon, then an oxygen, then an oxygen, then an OH. But most of the time, we'll kind of give you the structure if it's something wonky like that. If it's just PCl3, then it's just P and then Cl attached to all of them. That's a great question. So when comparing N to Cl and N to N, did it give you electronegativity values for these? Probably did. I'll look them up real quick, so I'm not lying to you. I think I remember seeing that question, so I just want to make sure that okay, so when we're looking at these two, nitrogen has 3, and then chlorine has an electronegativity of 3 as well. Okay, so right, you do have to look at the values given. This specific question did not give you the electronegativities. However, that was in a different question where it told you the values. But they are right. Chlorine is right underneath fluorine, and then nitrogen is 2 over. So since chlorine's a little bit bigger, being 1 period down the periodic table, they're about the same. So in this case, they're both 3. So when we're looking at the nitrogen and chlorine bond, is that a polar bond? No, it's not, right? This is 3 and this is 3. There's no difference in electronegativity. And so there's no pull of one atom over the other to have the electrons more. So this is non-polar. What about nitrogen? Nitrogen's 3. Nitrogen's 3. What happens to this bond here? Is that polar or nonpolar? That's nonpolar as well, right? So we're comparing two nonpolar bonds. What this then comes down to is 1, the size of our atoms, and 2, how long the atom is, or excuse me, how long the bond is, and then how many bonds are we actually breaking. So nitrogen having 3 bonds is like if you are in karate class and you're trying to break 3 boards at one time. Is it easier to break 3 boards or 1 board? It's easier to break 1, right? Or if you have a pencil and you're trying to snap that in half, it's easier to break that 1 pencil in half than 3 at one time. So since that single bond is easier to break, nitrogen with 3 bonds is going to require more energy to break. Okay, so you were close. When we have, right, nitrogen and nitrogen, 3 bonds means you have like 3 leashes, right? So that is a really tight bond between them. When you have 2 bonds, that's like 2 leashes, and if you have 1, that's just 1 leash. So the more bonds between a molecule you have, the stronger the holds those elements have on each other. And the greater the sharing and the greater the energy of that bond between them. So that makes it harder to break because you have to put more energy into those bonds. Does that make sense why the N3 would be? I'm always coming up with some, right? I have a couple, right? You can think of boards, you can think of pencils, or you can think of a dog on a leash, right? If you have a dog on a leash with 3 leashes, it's not going to get very far away. Yep. Are there any other questions on like the bond breakage and stuff between that? The other half of that question was how long the bond was. As your elements get bigger, right, that's going to put more space between the atoms. So, or that's going to put more space between the center of those atoms, right? If you have nitrogen and nitrogen, those are the same. That's your distance between them. If you have nitrogen and chlorine, we now have a longer distance between those atoms, and so therefore that bond is going to be longer. So the bigger the atom, which means as you're going down the periodic table, the bigger the bond between them. Okay, and then I'll look at the Lewis structure one. Okay, so yeah, of course. So for this question, we have, right, where we have EO F minus, F2 F minus, and EF5. Okay, so you have these two. Was this the question that you were thinking of? Right. So you have these two structures here, and they said that the oxygen or the O's and the F's are oxygens and fluorines. So The big thing to look at here is how many electrons are in your entire system. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17. We have 28 total electrons. We had one oxygen atom. So how many electrons are in oxygen? Good. And we had 2 fluorines. So how many electrons are in fluorine? Good. So this was 20 electrons. And then we also know that we have a minus for our atom or for our element. So what do we need to add up 1 additional electron. So that's going to be 1. So 20 and 1 is going to be 21 electrons used up from the oxygens, the fluorines, and that extra electron, which means that we have 7 electrons remaining. Yep, so we want something that has 7 electrons. And then in your question, you're given bromine, which has 7, sulfur, which has 6, fluorine that has 7, lead that has something I forget, and phosphorus that has 5. So based off of the first structure, you have bromine or fluorine that center one could be. Okay. Fluorine should jump out as something that probably is not going to be it because it's the most electronegative, so that's hardly ever the center of your atom. However, based off of the second structure, what is our E element doing? How many bonds does it have? Or how many electron domains does it have? It has 6, right? 6 electron domains. So we call that expanding the octet. Can fluorine expand its octet? Is fluorine able to make 6 bonds? No, it cannot make 6 bonds. So since our E is forming 6 bonds and we know this can't form 6 bonds, we know that bromine has to be our answer because that can expand its octet and it has 7 electrons. Questions there? Does that help with that question? Great. Okay, any other questions that we have? Yep. So when we look at quantum numbers, right, we have N, L, M sub L, and M sub S. Okay, so for our quantum numbers, L or N is going to be your energy level. And our rules for this is this has to be an integer greater than or equal to 1. Okay. So that's n. So options are 1, 2, 3, 4, 5. L, does anyone remember what L is? Yep, this is going to be our shape, or our subshell. And right, so does anyone remember our rule for L? Yep, so this is going to correspond to SPDF. So, right, we have SPDF, and this is n minus 1. Right, so if, as an example, if n is equal to 4, L is equal to 3, 2, 1, or 0. Right, all of those options exist. If n is equal to 1, then L can only equal 0. Okay, and then corresponding to SPDF, S is L equals 0, P is L is equal to 1, D is L is equal to 2, and F is L is equal to 3. Okay, questions there? Okay. M sub L is equal to, does anyone remember? Does anyone remember? You'll have like the equations for wavelength and frequency compared to speed of light. And I think you do get nanometers here. 1 meter to nanometers, which should be helpful for wavelength. Okay, so M sub L, this is going to be your orientation slash your orbital. And the rule here is negative L is less than 0, greater than equal to 0. Right, integers from negative L to L. So, right, as an example, if L is equal to 2, M sub L equals negative 2, negative 1, 0, 1, 2. Okay, questions there? Right, then the last one is M sub S, and this is going to be your spin. And this is plus or minus 1/2. And everything that we need to know is that electrons have to have different spins. And does that help with quantum numbers and orbitals? Are there any? Yep. Any other questions on those? Yep, so when we look at lithium, this is 1s2. Let me do a different one. When we look at helium, this is just 1s2. So the quantum numbers for, which means that we have an upspin and a downspin in its orbital. So that means if we're looking at quantum numbers, we can have 1, 0, 0, plus 1/2, which would correspond to the upspin, or we can have 0, 1, 0, 0, minus 1/2, which would correspond to the downspin. So in these two electrons, this one corresponds to this, and this one corresponds to that. So that shows that they have different spins and different quantum numbers, because no electron can have the same quantum number. It's like a way, it's like finding hide and seek, where it's like, oh, I'm picking this electron, and so you go and you find that specific electron based off of the parameters and the numbers given. That's a great question. So when drawing a Lewis structure, how do you determine which element to change to a double or triple bond first if there are multiple elements? Pick the least electron or the most electronegative first. And then depending on the formal charge of that element, if it's like really far away, then do that one first. Yes. Yep. Um, I would fully commit to it, I would say. No, don't fully commit. Um, don't fully commit. Try and do double bonds first, right? Because if we look at something where it's right, if we look at carbon dioxide, here we see that, right, carbon does not have a full octet. So we're going to take one oxygen and make it a double bond, therefore creating this one here. Oxygen, right, carbon still does not have a full octet. So if I were to make this a triple bond, then this becomes this here. And although technically a valid structure, this has a +1 formal charge and this has a -1 formal charge, and we don't like that. We would prefer this to actually be this here, where now the double bonds are spread out. And now there is no formal charge on any of the elements. Yep. And everyone remembers how to calculate formal charge? Formal charge is equal to the valence electrons minus the lines plus the dots. Quantum mechanics, probably not a lot. I would look at the practice exam, and if there's any sort of quantum mechanics on the practice exam, then that's probably the same flavor that you would see on the regular exam. Any other questions? Everything after exam 1. So I think electromagnetics or the electromagnetic spectrum, Lewis structures, like quantum numbers, periodic trends. Big stuff there. Think like, what is that, unit 5 and 6? Yeah, I would say a lot of electromagnetic spectrum, intermolecular forces, right, phase diagrams, Lewis structures, polarity is a big one. Yeah, everything. Probably a lot of chapter 5 or unit 5. Yep, I think that's fine. Electronegativity, right, is just you usually will be given values for that if needed. So you don't need to know that too much, but if you know that the most electronegative is in the top right corner and the least electronegative is in the bottom left corner, then you should get that trend there as well. Any other questions? Yes, yep, they do. Ionization energy, just remember, right, that has to deal with the electrons. So I feel a sneeze. So when you look at right, it's period 3. Yeah. So when you look at it this way, this one is 3s1, 3s2, 3p1, 3p2, 3p. So if we're looking at right, this here, it is easier to remove this electron in the p orbital than it is to remove this electron here in the s orbital, right? That one unpaired electron is easier to remove than the paired electron. So if we look at ionization energies, it's like sodium, magnesium, and then aluminum goes down. And then it's silicon and phosphorus, and then it goes down for sulfur, and then back up for chlorine, and then argon is up here. Right? It goes down, up, because at sulfur, that unpaired or this paired electron here can easily be removed to allow for 3 unpaired electrons rather than 2 unpaired and 1 paired. So it drops down. So your trend is like a zigzag that way. So overall, same trend as it goes up as you go across the periodic table, but just know that there's slight nuances across. course, it is pretty interesting. And that happens for all of the periods too. So as you go across, that happens as a trend every time. It's all about the atom remaining as least high energy as possible. Anything else we want to discuss today? Yeah, great. Thanks for coming. And then I'll probably do a Zoom review on Sunday night to do last minute final or last final exam question. So I'll send out another Zoom link for that one if you want to attend. Have a great rest of your day. Have a great rest of your week. Thanks for coming.